All right, we're going to talk about three different types of solubility solubility problems that you might run into in this class. Traditionally, let's say we have a solution that is barium iodate, and barium iodate is sparingly soluble, meaning if you put it in water, it doesn't fully break apart into all barium and all iodate ions like you would if you had something that was highly soluble. So when you run into something that doesn't break apart in water, in other words, what I mean by that is if you put some barium iodate into water, you'll get some barium ions and some iodate ions. But for the most part, they'll stick together, meaning this barium will hang out with two iodates. And that means that they'll be a solid and generally fall out of solution somehow. So the KSP for barium iodate is 1.5 times 10 to the negative 9. And what that equals is the maximum concentration that these can possibly be in solution before they start falling out and making a solid. So in any given situation, that would be the barium times the IO3 negative squared. And that's simply because of the way this breaks down. So in solution, you'd have this breaking down into barium 2 plus and 2 iodates. So this is simply an equilibrium equation, and of course we would exclude this guy because it is a solid. All right, so if we were solving for standard molar solubility, we would set that 1.5 times 10 to the negative 9 equal to x times some 2x squared. That's because for every one of these we dissolve, we get one of those and two of these. And so when we put these here, if you kind of work your way through it, you'll find out that that 1.5 times 10 to the 9 is equal to 4x cubed. That's because this 2 goes there, and that 2 goes there, and so it ends up being 4x squared times an x is 4x cubed. And if you solve for x, you'll find out that x is equal to 7.21 times 10 to the negative 4. All right, so this would be a standard solution, and the simple question would be like, what is the molar solubility? Okay, so that's all grand, but what happens in a different situation? So for example, what happens if I were to take and add a whole bunch of barium to this solution? Barium, for example, let's just say barium nitrate. So if I added a whole bunch of barium nitrate, that would break down into barium and nitrate ions. And traditionally, we would look at this as what's called the common ion effect, because we're adding an ion that's exactly the same as one that's already in there. So let's go ahead and make this into a problem. Let's say I was asking for what is the molar solubility of barium iodate now in a solution of 0.0150 molar barium nitrate. Okay, so now we're saying, all right, we add a whole bunch of barium to this, 0.0150 mole per liter. What's going to happen now? Well, logistically, and due to Le Chatelier's principle, if we add barium nitrate over here, or actually, let's look at the equilibrium reaction. If I add barium nitrate over here, what should happen is the reaction should go this way, due to Le Chatelier's principle. So our concentration should, in fact, actually go down. So let's see if that happens. There's going to be two ways we're going to calculate this. So first is with activity, and this one is without activity. So this is more of our traditional approach. It's easy and it gives us a good estimate, not an appropriate estimate, but at least pretty close. Okay, so to solve this, let's go ahead and look at the reaction again. And it helps to draw an ice table in this situation, I think. our initial concentration would be nothing because this is a solid, but our initial concentration of barium in this case, if we're talking about having a bunch of barium nitrate in there, would be whatever the concentration of barium nitrate is, because it's a 1-to-1. So in this case, we'd have 0.0150 mole per liter. Now, our change, once we have barium nitrate that starts to dissolve, it will add some barium ions, and it'll, for every one of those, it will add 2 of the iodate ions. And now at equilibrium, we just add them up. But there's this great, wonderful thing, which is, if you look up here, this is 7.21 times 10 to the negative 4. That's a relatively small number. And so over here, compared to this 0.150, we're going to go ahead and assume that this one is relatively small. And that keeps us from having to do the quadratic equation, which is always kind of grand. Although sometimes, if this isn't very small, we would have to go about doing a quadratic equation. So now we can go ahead and solve for this. Our KSP again is 1.5 times 10 to the negative 9, and it's equal to 0.150 times x. Or excuse me, 0.150. I can do it. Times 2x. Let me go ahead and write that again so it's a little prettier. 0.0150 times 2x. That should be squared. And now we're going to go ahead and solve for x. Our x in this situation will be equal, ending up equal to the barium iodate concentration. When we solve for x, we get an answer of 1.58 times 10 to the negative 4. And effectively, that proved to us that by adding some more barium to the solution through the barium nitrate here, we have effectively decreased the amount that will actually solubilize inside solution. So that's grand, but we can make it even one step closer to perfection. And that is using activity. So what happens in solution is we've got these barium ions, and we've got iodate ions. And if you take a closer look at them, as soon as you put them into solution, they're usually surrounded by water. But we said, hey, we're adding barium nitrate, right? Now you would expect the nitrate to be inert, because it's not a common ion, it shouldn't have an effect. But the truth of the matter is the nitrate surrounds this barium. And forms what's called an ion sphere. And what's going to happen is it surrounds it so much that it keeps the iodate from coming over to react with the barium. And the same exact situation happens with the iodate, where it's surrounded by barium ions. So when this one's not allowed to come in contact with this one, the barium and the iodate can't come into contact, they can't fall out of solution and form a precipitate. So essentially, we have to say, hey, anytime they're surrounded by some kind of ion, we can't count them into the reaction at all. It's not really fair. And so what we do is we use what's called the activity, which takes into account that effect. So in order to figure it out, you first have to find the ionic strength. And the ionic strength is mu, and it's equal essentially to the sum of all the concentrations of the ions times the charge of the ions squared. And you're going to go ahead and take that times 1/2. So the ions that are in this solution right now that we know about are the barium and the nitrate, because those were the soluble ones. We wouldn't include the barium and the iodate from the barium iodate because it's a very, very small amount, and we don't even know how much would be solubilized in there. So we're going to go ahead and start with just the barium and the nitrate. Remember, barium nitrate breaks down into barium and 2 nitrates. So let's go ahead and look at these charges. We knew that we added, if you remember, a concentration of 0.150 mole per liter barium nitrate. So we're going to use this concentration here. So let's go ahead and start with the barium concentration. That's 0.0150 times its charge squared. Well, it has a positive 2 charge, so let's square it, plus that of the nitrate. So for every 1 barium, there's 2 nitrates. So our concentration for nitrate is twice that of this. So it's going to be 0.0300 times its concentration, which is -1, squared. And all this in here in the parentheses equals I think it's 0.090. And when we divide it by 2, because we multiply it by 1/2, we get an answer of 0.045, which will round to 1 sig fig as 0.05 mole per liter. And that ends up being our ionic strength. That's important because that helps us determine the activity coefficient. And here's where activity coefficient comes into play. In our previous question, we determined that the KSP was equal to concentration of barium times the concentration of iodate squared. But activity tells us that the truth is it's equal to the concentration of barium times the activity of barium plus the concentration of the iodate squared times the activity of iodate squared. And so now we have to take into account these little activity, and I shouldn't say activity, I should say activity coefficients. And the way we take those activity coefficients is essentially just by using a simple table that relates the ionic strength to the activity coefficients. So if we go ahead and plug this in, we'll start with the barium concentration. The barium concentration, we know it's 0.0150. Again, that's coming from the barium nitrate. That's our barium, the barium nitrate, because the barium from the barium iodate would be very, very small, times the activity coefficient of barium. So we can pull up a table. It's going to be a real common table. And if you look for barium, it's right here in the +2. And then we go over and we also look for something with an ionic strength of 0.05, which we had. And we get an answer of 0.465. So that's why right here we'll plug in 0.465. Now we've got our iodate concentration. Our iodate concentration we don't know. I'm going to keep it as this. It's going to be our X squared. But we can find the activity coefficient for iodate by looking at the table. So if you look in the -1s, let's see where I can find it. You might have found it faster than me. There we go. It's right there. And then over here to our 0.05, I get an answer of 0.82. So our activity here, coefficient here, will be 0.82. And don't forget to square it. It's an easy mistake to make. All right. So once we're here, we have to just remember that our KSP was 1.5 times 10 to the -9. And we can solve for our iodate concentration very, very quickly. Simply make this an X in your equation. And if you do that, you get an answer of 5.65 times 10 to the -4. Now that was our iodate concentration. The question originally asked for the barium iodate solubility. So for every one of these, or every 2 of these, we had 1 of these. So we eventually just have to divide it by 2. So we can just look at it this way. We know for every 2 iodates, we had 1 barium iodate. And if we do this, we get an answer of 2.78 times 10 to the -4 mole per liter. So let's talk about these differences. This concentration should have gone up from the last one. And in fact, it did. When we didn't have activity in mind at all, it was 1.5 times 10 to the -4. But now that we took activity into account, it's 2.78 times 10 to the negative 4. The reason for that is these numbers went down, which effectively meant these have to go up. And that's because we're removing these from solution. So as we remove these from solution, more and more and more stuff has to dissolve to keep this equilibrium constant and the equilibrium coefficient exactly the same. And that's what happens. So, yep, have a good day.